In this video, we are going to look at the properties of determinants of a matrix. And so none of this shenanigans should be here. It should be looking at the properties of determinants. So whatever, it's all good. The determinant of the identity matrix of size n is 1. The determinant of the elementary matrix in which two rows are interchanged will be -1. The determinant of the elementary matrix that is multiplied, which is basically the identity matrix multiplied by alpha, is one row by alpha, is going to be equal to alpha. Then the determinant of the elementary matrix in which two rows are added together and then also multiplied by alpha and then put back into another row. So alpha times row I and then added to row j ends up becoming just 1. And then if we have a square matrix where there's one row or one column of zeros, the entire row or column is zeros, then the determinant ends up becoming 0. So that's nice. If A is a square matrix with two equal rows and two equal columns, the determinant is also equal to 0. If A is a square matrix and B is a square matrix by interchanging two rows or two columns, then the determinant of A is going to be equal to the negative determinant of B. And that's something similar to up here if two rows are interchanged. If A is a square matrix and B is obtained by multiplying a row by alpha, that's something similar to this, and then we have the determinant of A is going to be alpha times the determinant of B. So in other words, the determinant of B is going to be the determinant of A times alpha. If A is a square matrix and B is obtained by multiplying a row or a column by alpha and then adding it to that row or column or to another row or column, then the determinant of A will be exactly what we started out with, which is the determinant of B. I know there's a lot here. Moving on, if A is a square matrix of size n and E is an elementary matrix of size n, then I can find the determinant by first multiplying them, or I can find the determinant of each one individually and multiplying those two answers together. If A and B are square matrices of size n, then I can multiply those two matrices first and then find the determinant, or I can find the determinant of each one of them individually and then multiply those two answers. And lastly, for now, if A is a square matrix of size n, then A is singular if and only if the determinant of A is equal to 0. All the formal proofs and theorems are in your book for your viewing pleasure. Please go take a look. Let's start doing some examples now. So we look at our first example here and it says, hey, here is matrix A, here is matrix B, and these are the things that I did to A to get to B. I interchanged row 1 and row 3. I multiplied row 2 by 1/3. And I added -2 times row 1 to row 3. And so I'd find the determinant of this, my usual way of finding the determinant. In this case, I'm going to multiply down in that and then, add that augment on that first two columns, and I get -99. Then I do the determinant of B, and I get +99. And that is because I had that row with an alpha. I also had a multiplication of 2 times another one, divide, and then adding two rows. So pretty much all I ended up really doing is just interchanging the two rows, and that's how come the determinant ends up just being the opposite sign. Let's take a look at my next example here. With my next example, I have this matrix. And with this matrix, one of the other things that we end up with is the upper and lower triangles. I think we talked about that on my previous video. This is an upper triangular matrix, which means the determinant is just going straight down the diagonal. That should have been one of my theorems or proofs up there. I guess I just either talked about it before or it wasn't that important, I guess. I don't know. Anyways, moving on, we have the determinant of A times B is equal to the determinant of A multiplied by the determinant of B. Here is A and here is B. The determinant of A is -1, a nice little loop that we make. The determinant of B is again a nice little loop we make. If we multiply these two together, we are going to get +7. I can also do it by multiplying these two matrices together and get this matrix. And then when I do its determinant, doing that little loop, I have -5 times 0, -7 times 1, which gives me +7. So you can see that I can do the determinants first and then multiply them, or I can multiply them and then find the determinant of that resulting matrix. Here is my next one. My next one is this. I have my matrix A, which is an elementary matrix with one row interchanged. Row 1 and row 2 were interchanged, and since we know by all of my theorems, the outcomes of my theorems before up above, is that if I interchange 2 rows on my elementary matrix from my identity to my elementary matrix, we know the determinant of this new matrix is going to be -1. Moving on is another example, and a little more abstract. So suppose we have this matrix. We don't know what the entries are, and we really don't care, but we do know the determinant is equal to 3. Then, to find this determinant, I look at what is difference between what I started out with and what this is. You can see for this first matrix, all I've done is interchange row 1 and row 2. So the determinant of this new matrix has to be the opposite sign, so -3. And for this matrix, what I've done is I've added 2 rows, and then I've multiplied a row by -2. The fact that I added 2 rows and put it back into that same row does not change my determinant. What changed my determinant is the fact that I took -2 times row 2 and put it back into row 2. So I've done that alpha multiplied by a row, which means the end result would be that alpha, which is -2, multiplied by the determinant, so that ends up becoming -6. Now let's take a look at this example here in which I have this matrix, and you can see this row matches this row. Because this matches this row, we know the determinant will be 0. From all of these theorems, we end up with a new round of non-singular matrix C equivalents. We know A is non-singular, and these are all equivalent. Then A row reduces to the identity matrix, which we knew. The null space of A contains only the 0 vector, which we knew. The linear system has a unique solution. We knew that too. The columns of A are linearly independent. Still nothing new. A is invertible. We established that. The column space of A is Cn, which we've established. The columns of A are the basis for Cn. We've established that too. The rank of A is n, which we've established. The nullity of A is 0, which we established, but here's what we finally pick up. The determinant of A is non-zero. If it is non-singular, the determinant of A cannot be equal to 0. We also get a couple of more outcomes, which is, check this out, man. If A is an invertible matrix, then I can find the inverse by doing 1 over the determinant multiplied by the adjoint of A, where remember, if you remember the adjoint, it is the conjugate transpose of A. So here's a quick way now to find the inverse without having to do all those row operations that we did when we augmented on the identity matrix. Way easier. Now, determinants in and of themselves are pretty interesting, but there are some real-life applications. So let's take a look at some of the applications. Suppose we have this quadrilateral and we want to find the area of the quadrilateral. Then what we do is we cut it into 2 triangles. My first triangle starts at O, goes to A, and ends at B. I have this ordered pair at A, which is 1, 2, 1, 2. I have this ordered pair over here, which is 4, 3, 4, 3. Then the area is going to be 1/2 the determinant of that matrix, so it ends up being 5/2. And then I have this matrix, and its ordered pairs are 4, 3, 4, 3, and then 3, -1, 3, -1, and then when I do its determinant, and you're thinking, wait a minute, couldn't I have done 3, -1 in the top row? Sure. It doesn't matter because it ends up being, you're still going to multiply the same numbers together, and you're still going to take the absolute value of it, it's the absolute value, and it doesn't matter. So now that I've broken it up into these 2 triangles, then my determinants ends up being 5/2 and 13/2. I add those together, and my answer is 9 units squared. So a really nice application of determinants. Another application of determinants is solving systems of equations by using something called Cramer's rule. And what Cramer's rule does is it says, let's find the determinant of this A sub I. What A sub I is I take my A matrix, and my A matrix for this particular example would have been 3, -1, 0, 1, 2, -1, 0, 1, and 2. That is my coefficient matrix. So here is my A matrix. Here is my B matrix. Then A1 means that I take row 1 right here and replace row 1 with my B vector. A2 is I replace my second row with my B vector. And A3 is I replace my third row. I replace my column, these are all columns, with my B vector. So A1, I replace my first column with my B vector. A2 as I replace my second column with my B vector. A3 is I replace my third column with my B vector, and I found the determinants. I will find the determinants of each one of these new matrices. I then divide it by the determinant of my coefficient matrix. Once I do that, I can tell you what x sub 1 is, x sub 2 is, and x sub 3. X sub 2 is going to be the determinant of this A2 matrix divided by the determinant of the coefficient matrix. And A3, which gives me the x3, is the determinant of A3 divided by the determinant of my A matrix. And so there is my solution. And I didn't have to do it by inverting. I didn't have to do it by doing the row reduced echelon form. I was able to do it by determinants. So here's another application of determinants.